This is another LeetCode medium question named beautiful arrangement that we want to cover today. In this question, you are given an integer n, and you need to find out the number of permutations each satisfies the following condition. For the ith element in the permutation, either it is divisible by I or it divides I. And the only constraint we know is that n is going to be less than or equal to 15. Now let's see how we can solve this problem. To me, the most straightforward solution is to do a full permutations. What I want to do is, as it says, I want to do all permutations of 1 to 15. So once I find out all the permutations, then for each permutation, I can do a check to make sure if it qualifies the condition. How many permutations do we need to take into account? The number is exactly 15 factorial. And how about a check? Because for each permutation, you need to check each element in the permutation. This will be 15 itself. Now, what's the scale of 15 factorial? If you use Google or any calculator, you'll know that it is around 10 to the 12. Eventually, our time complexity for this solution will be around 10 to the 13th. Is this good enough? Again, for C++ or any compiled languages, it can handle around 10 to the 8 to 10 to the 9th operations per second. However, for Python or any non-compiled languages, it can only handle around 10 to the 6 to 10 to the 7 operations per second. But no matter which language we use, this is still a big difference. Unfortunately, this solution is not good enough to be used in practice. The reason why an algorithm runs slower than desired is usually due to the fact that we have done extra but unnecessary steps. If we can identify what they are, then we will know in which direction we can improve our algorithm. In this specific algorithm, we know that we enumerate all the permutations, which include many permutations start with 1 and 3, and followed by the rest of 13 digits. Now, if we can somehow enumerate the possibilities from left to right, then we will have known that the digit 3 at position 2 is position 2, position 1. The 3 at position 2 does not satisfy the condition. Basically, we can start very, very early, and we can save a lot of computations here. We can save 13 factorial computation here. That's going to be a huge save in the overall complexity. This is basically the motivation we want to improve our algorithm. All right, now let's take a look at how we can do it in practice. In terms of the second solution, I'm going to call it early stop permutations. What I want to do is to introduce a recursive function and do exactly what I said before. Now let's think about the parameters we want to take into this function. I need to know which position I'm in right now. I also want to know which digits have been used and which have not been used. I will need to at least have two parameters, positions and the status of digits. What I want to return from this function is the number of permutations after I select this digit and move on to the next position given this status. The output is just an integer, and the number of valid permutations. There's a very obvious corner case, which is when the position equals to n, where n is the number of digits, then we'll return 1. It means that it's a valid case. Otherwise, I will have a for loop here. I would like to enumerate all the possible digits, so I will do index from 1 to 15. And then for each index, I would like to do a check. If the current status of this index has not been used, and this digit at this position is actually valid, I will first kind of take over this digit here. So I'm going to set this availability to false. And I will dig deeper into this function. I will move on to position +1, and then also forward the updated status to the next function. And after it returns, it will give me the number of valid permutations. I will just update it in this like a counter, just a variables for me to know the accumulated number of valid permutations. And of course, in the very beginning, I should have like a counter on this, right? So you should start with 0, and I'll keep updating it for every valid digit I want to use here. And after that, I also want to release the takeover of this digit. So I'll set it to true. Now at the end, I will just return the count here, which is again the number of valid permutations at this position at this status. Now let's think about the improvement. How much did we improve with this algorithm? Unfortunately, there is no concrete number I can provide here, but we can have a very rough estimation. Let's first think about the first solution. In the first solution, we have 15 digits available at index 1. This is the index to 15. We have 14 possible candidates at the second index, and so on. And at the end, we have only one candidate. The number of permutations we need to check here is 15 factorial. Now, in the second solution, we also have 15 candidates at the first position, but we only have 7 candidates at the second position. In fact, we only have 5 digits at the third position, and so on. Even though I don't know exactly the permutations I need to check here, but it's a lot smaller. We know that there's a huge improvement from solution 1 to solution 2, but there are still places that I can improve this solution. Let's check them out. Now I'm going to use a slightly different example to demonstrate what I mean. Assuming that I already enumerate 1, 2, I have used 3 digits here, and now I'm at the 4th position, and I would like to use digit 4 and move on to the 5th position. This is where I am. When I first do this, the status I have is 5 to 15 digits available, and now I'm at position 5, right? So this is basically the computation I need to do. I will go all the way down to the end and get a number back from this recursive function. Later on, I will also enumerate another possibility, which is 3, 2, 1. And let's say I decide to use the same 4 digit at the 4th position, and I decide to move on to the 5th position. Okay, guess what? This is exactly the same computation we have done before. If I don't do anything here, if I keep using this early start permutations, I need to again enumerate all the possibilities with these 11 digits. So that's like an improved version of 11 factorial. There are still quite some computations I need to do there. However, we actually already calculated this result before. Why can't we just reuse it? What I want to do here is that I want to memorize the computations that I have done before. I want to reuse the results. That's basically the improvement I want to do here. I want to save this result somewhere such that I can reuse. This should give me O1. I want to do this in O1. What are the changes I need to make here? Let's call it the third solution. This is actually the dynamic program. The thing I need to change is actually pretty easy. Instead of return the count value here directly, I will need to remember the results. I will say record, position, and status goes to count. And then I return the results. And also here, before actually going to the calculation, I will do a check here. If the position and status is already in the record, it means that we have visited this position status pair before, and we should just return the result directly. Now, let's actually do a quick analysis on the time complexity. So we know that in the first solution, the complexity is pretty straightforward. It's 15 factorial, or it's n factorial, right? In the second solution, we know that we make some improvement there, but it's hard to measure the exact improvement. I will call it improved n factorial. And now for this solution, let's think about its complexity. We know that for each position status pair, we'll only visit it once. We have 15 times the status is, for each digit, its status is either available or not available. So we have 2 to the number of digits status. This is all the possible status for the digits. We have so many unique pairs of values we need to fill in. And then in each recursive function, we'll need to go through a for loop up to 15 elements. That's the complexity. And if you do some calculation, this is around 10 to the 6 complexity. But if we write it down in a formal way, then the complexity is n squared times 2 to the n. This is the complexity we're talking about. By just adding these few lines of codes, we actually improve our time complexity by a lot. This is the dynamic programming solution. And now let's jump into the coding part. Previously, we talked about 3 different solutions: the full permutations, the early stop permutations, and the dynamic programming. Given that the full permutations is too slow to be practical, I'm going to focus on the last 2 parts. I'll start with a solution with only a recursive function and see how fast it is. Later on, I will add a memorization part to prevent repeated calculations and observe the improvement. I would like to start with introducing a recursive function called search. We will take 2 parameters. One is a position, and the other one is the status, which is a list of boolean to indicate the availability of the digits. At the end, it should return an integer, which means the number of valid permutations from this position on, given the status. There is a very obvious current case where position is already at the end of the array. When that happens, I should just return 1 because we find a valid permutation. Now, of course, in order to use the int here, we still need to do assignment here. In each recursive function, we'll try to use each of the digits. I will first iterate through all the digits, and I'll do a check here. I can use a digit if it is not yet used, and it satisfies one of the conditions. The first condition is the position plus 1. I need to make it 1 index moved by index plus 1. I also need to make it 1 index. It's 0. The other condition is the opposite. Right? So index plus 1 mode position plus 1 equals to 0. If either of the condition is true and this digit is not yet used, then I'll try to use it. I will put status index equals to true to try to take over it. Now, of course, I will need to revert my takeover later. But while I'm taking over it, I can dig deeper into the next position. I will do self.search position plus 1 and with my updated status. This recursive function will return the number of valid permutations from this point on, right? So I will have to accumulate the number of valid permutations in a variable. I will have a counter starting with 0. At the end of it, I will just return the counter itself. That's the implementation of the recursive function. Now, I just need to make a code to the recursive function correctly. I will start with position 0, a list of both instances for underscore in range 15. I will just return this result. Now, let's give it a try and see if it works correctly. Right, yeah, it seems that it passed the test cases. And let's submit the answer. Right, so you can see this performance is right around here, which is not too bad, right? So it passed like 56% of the users. Actually, this should be self.n instead of 15. Now, just out of curiosity, I would like to know how many operations we actually did within this algorithm. So in order to know that number, I can introduce a new variable called number of operations and set it to 0. And within each recursive function, I will just increment this value here. It should be plus equals to 1. Because each for loop, we actually did something, right? So it makes sense to increment value here. And I would like to print out the number. So we need to first memorize the results in a variable here, print out the number of operations, and then actually return results. So let's see how we got here. For 2, the operation is only 6. If I change it to 15, and let's give it a try. You can see the number is around 10 million, right? So it's 10 to the 7th, which is pretty slow. And it's already at the age of what Python can handle in a second. Now let's see how we can improve this solution. To improve the complexity of this algorithm, we say that there's a dynamic programming solution. In order to use dynamic programming, we need to first introduce a dictionary to memorize the results. So let's call it a dictionary here. And what the dictionary will take as a key should be the pair of position status. We need to make status a tuple. So let me call it status tuple equals to status. And after that, I can check if this paired status tuple is inside the self.directory. If it does, then I can just return the result. If it does not, then I will need to do all the calculations here and memorize it at the end. Right? So I will do this guy equals to count and return count. Just introducing this row and these two rows, we've basically finished the memorization. And now let's do it again to see how much operations we need to do with number 15. Now the results got reduced to less than a million, right? It's actually around a quarter of a million. So you can see the improvement here is huge, right? And also let's submit the result and see the improvement in the percentage. Now I can beat around 85% of users. And the speed, you can see, I think improved from around 600, 700 milliseconds to only 100 milliseconds. So improvement is like 5x. Cool. So that concludes our video today, and thank you for watching.